Welcome to this video on predictive maintenance using machine learning. Predictive maintenance is a technique that uses data analysis and machine learning to anticipate equipment failures before they occur. This approach allows companies to reduce downtime and optimize maintenance schedules, ensuring smooth and efficient operations. For example, in manufacturing, predictive maintenance can help identify when a motor might be about to fail by analyzing vibration data and allowing repairs before breakdown. In the aviation industry, it can predict wear and tear on aircraft engines, enabling timely maintenance and reducing the risk of unexpected failures. In this class, I taught my students about the ecosystem for training an AI algorithm using SAINT microelectronics technology. Now, I'm sharing the step-by-step process with you. We'll use a Proteus evaluation board, the ST-Link Mini interface, a small USB fan, the ST-Link 009 drivers, and the Nano Edge Studio software from ST Microelectronics. Let's get started. Step 1. Download and install the ST-Link drivers STSW-Link 009. Step 2. Download and install the Nano Edge Studio software, which is the artificial intelligence software we will use to train the anomaly detector. Step 3. It is now time to configure the hardware. We will use the Stival PROTEUS1, which is an industrial sensor evaluation kit for condition monitoring, based on the 2.4 GHz STM32WB5 module. Please download the documentation and the instructions for assembling the sensor hardware. This sensor module features accelerometers, gyroscopes, and temperature sensors, among other advanced MEMS sensors that we will use. In the PCB circuit, we can see the connectors for USB data and the power supply, the battery ST-Link Mini, the power button, and the locations of the MEMS sensors. Step 4. The connection setup is displayed in the figure. Please connect the USB data cable to the PC and to the ST-Link Mini, which must be connected to the Proteus board with a 14-pin flat cable as shown. Step 5. Launch Nano Edge Studio and choose the data logger option. Then, search for and select the Proteus board. Step 6. It is time to flash the board. Unzip the data logger file and copy the bin file as shown. Step 7. In Nano Edge Studio, navigate to the home page and select the anomaly detection option to start a new project. Please enter a name for the project and select Proteus as the target board. Step 8. Now, let's input the normal or regular signals, those we consider to represent healthy behavior. Note that Nano Edge will arrange the input signals in rows instead of columns. This format is used by Nano Edge as the input tensor for training the machine learning algorithm. I securely attached the Protea sensor to the fan using straps to record the regular signals. While the fan is running, the Nano Edge collects 100 data lines to simplify the experiment and reduce the time needed. Step 9. Record the anomaly signals while gently perturbing the fan with a cardboard stick or any soft stick. The goal is to create unhealthy signals that we can use to train the machine learning algorithm to classify as abnormal. Step 10. Train the machine learning algorithm using a benchmark system provided by Nano Edge Studio. The benchmark will train several algorithms to choose the better one in the context of anomaly detection. This step is time consumption intensive because the benchmark tests out several algorithms varying their hyperparameters that are displayed as tested libraries. After 49 minutes, the benchmark report indicates an accuracy score of 98.29%. It also highlights the RAM and flash memory resources required if an embedded system is used to deploy the model. The system recommends running 20 iterations or tests to validate the model and achieve the performance reached during the benchmark phase. It was calculated that a 0.9 millisecond inference time is achieved if an F411 microcontroller is used. Step 11. During the validation step, we selected a serial emulator marked with a crown signal, indicating it is the machine learning algorithm with the best performance. Next, we reconnect the fan and train the algorithm using 80 lines of normal signal data. When we click the Start Learning button, we turn on the fan and train the algorithm with these regular signals. After completing the 80 signals, we select the Go to Detection button. With the fan still running, we perturb it with a stick for a few seconds to observe the results. If this video was helpful, please like it and share it to help grow the embedded artificial intelligence community. Thank you.